The next speaker is Don Schneider. Don was a PhD student here. He was a student with Jim. He was a student with Jim Gunn, and then after he finished that work with Jim, well, it sort of continued. It never is finished, of course, but when he got his degree, he then went to work with Maarten, and after a couple of years at that, he went to Penn State, and he's been there ever since. Currently, Don is chair of the astronomy department at Penn State, very well known for his work on quasars, luminosity functions, and so on. And we got an advertisement, as it were, of what he's going to say. I actually don't know what Don's going to say, but Richard, I guess, did, and so he mentioned a couple of things. I'll just mention a personal note. In those days, when Don and Maarten and Jim were looking for quasars and whatever came by at the Palomar telescope at the 200-inch. I remember talking to them, to each of them. I'm not sure if it was collectively, I suppose one by one or whatever, and being really impressed at the idea of using the 200-inch telescope, just turn the thing off and let the sky drift by. And that was very impressive. Okay, so Don has talked, I don't know what his title is. What's your title?
Evolution of high-redshift
Quasar
quasars.
evolution at high-redshifts. Can you do it?
I don't know.
George,
Nope.
we need help.
I still run VMS, so I have a little difficulty here. My VMS laptop is this big, so I couldn't bring it along. Before I start, I'd like to tell two stories about Maarten. I see a number of young people in the audience, the importance of making good impressions, first impressions. Maarten was on sabbatical at the Institute for Advanced Study in 81, and he put out an advertisement for a postdoc, which I saw, and I applied. I hadn't worked on quasars, so I wasn't very optimistic of getting it. Looking at the faces here, does anyone remember the Bat Cave in Raleigh? Oh, a few people remember. There's a warren of offices known as the Bat Cave, and I inhabited it along with a number of other people. And the phone rang one day in March 1981. I picked up the phone and said, "Bat Cave." and there was silence. And the silence lasted for quite a while, and then I was just about to say hello, and then a very recognizable voice said, "May I speak to Donald Schneider? This is Maarten Schmidt." And I sat there thinking, should I say, "Just a minute, I will go and get him." So I still can see myself that instant thinking, "Oh, have I just done something?" Okay. The other was in early 1984. Marshall alluded to scanning the sky, and this Maarten and Jim Gunn, who was my thesis advisor, had been talking about using the CCDs, which we had an enormous CCD. It was 800 by 800, okay, and would cover 5 square arc minutes. And Maarten really wanted to look for high redshift quasars. When he asked me to work for him, he said, "Come and work for me, and in the next 3 years we'll find 50 redshift 4 quasars." I know you say you did say it, but you didn't know. And so I thought, wow, this is very exciting. But to do that, we needed to cover a lot of area. And so Jim said, "Why don't we try this TDI, time, delay, and integrate, to sweep through the sky?" Okay? And I will say, I do think that was really the inspiration for the Sloan Digital Sky Survey, that Maarten's work really got Jim really interested in this. So we spent a year in the hardware and the software, and we were convinced it was going to work. Okay? And so I was up in the prime focus cage, and Jim and Maarten were downstairs, and they said, "Okay, let's go scan the sky, rotate the pedestal," because I knew that we had to align, the stars had to go along the columns of the CCD, and so we had to go from our normal south to an east-west. So I said, "Don't worry, I'll rotate it." And so I did. We pushed the button, and we expected to see a tapestry of beautiful stars. Oh, Maarten remembers what we saw, yes. we expect to see this tapestry of stars go drifting through the screen. And what came up was, the universe was on LSD because all we saw were these long streaks everywhere. They were very narrow, very precisely aligned. And we just said, we have just spent a year and not done anything right. And then over the intercom, I hear, motion is a vector, Don. You have rotated it so that we're reading out the CCD this way, and the sky is going this way. So that was the beginning of our survey. Okay. Okay, so this is just a brief outline of the talk. I'll talk about the discovery of high-redshift quasars. What is a high-redshift quasar? 3C273 was a high-redshift quasar in its era. The path to redshift 3.5, and then the introduction of digital technology. Talk about the high-redshift quasar luminosity function, evolution of the accretion process, encountering the dark ages, and to redshift 7 and beyond. First, I want to show the impact that Maarten has had on our view of the universe. This is the timeline of the year of discovery versus the maximum lone quasar redshift. This is 3C273. This is shifted by 15 minutes. This is 3C48. The objects in red are the ones that Maarten discovered. And so you can see that he has 8 times found the most distant quasar. There was an early era here, and then this was the GRISM surveys that were done here. That I think is impressive, but when you look at, this is the age of the universe at the most distant known quasar. Okay, so this is kind of our grasp of cosmic time, if you want to see. And yes, we're all very proud of finding these redshift 4 quasars. But by 3C9, which I think is really an amazing paper, how Maarten bootstrapped all the way down to, carbon 4 and then Lyman-alpha, doing that without having, it's just, and there are no spectra published, or at least no tracings in that. I was hoping to show that. So you can see that, the first person to have the cosmic vision to go back over most of the age of the universe were due to Maarten's discoveries. And this is the logarithm of the volume of the universe. Okay, 3C273, 3C9. Well, we've been working since 1965, and we've made maybe a quarter of the distance that Maarten made in 1965. So it really is, that era in the early 60s really did open our view. I'd never heard the story, Maarten, when you talked about pacing that night and realizing that potentially you were going to be able to go to redshift 2 just from this, which really is the bulk of cosmic history. Okay, let me just, a brief history of the quest for the most distant quasar. Until 1987, the most distant known quasars were all identified by radio sources. In every case that there was a radio source, people went and looked at an object because it was a radio source. Okay? And it began with 3C273 all the way up to Parkes 2000 in 1982. In the 1980s, we got high-speed computers. I know, this is just amazing. I mean, we had a 1 megahertz computer. We were so excited by this. And scanned digital plates and CCDs, along with this enormous processing power, allowed large area red-sensitive surveys, because you had to get the red-sensitive because Lyman-alpha was now being shifted into the red. There was this object, Q1208, I think was by Cyril Hazard in 1987, optically selected, and they were optically selected all the way up until 1991 with PC1247. And then the SDSS, which again I think was due to the inspiration of Maarten's quasar survey. I'm sure you're all familiar with it. Multi-object spectroscopy up to 10,000 square degrees. From 1999 to 2002, the redshift went from 5 to 6.41. And then in the last 5 years, combining optical and infrared surveys, be able to have gone up to 6.43, and now the redshift record has gone over 7. I wanted to make a slide of what I considered the 10 people who had the biggest impact on the high redshift quasar universe, and of course Maarten. And Jeffrey Burbidge has been mentioned because of the great redshift controversy, but if you actually looked, he was our lead author or second author on many of those discoveries, those points, in the late 60s and 70s. So he was also out there working to find these distant objects to understand the early universe. This person, I think, is somewhat forgotten. Does anyone recognize him? Roger Lenz. He made one of the great discoveries, which I'll get to later. He had a multiple number of discoveries of the most distant object in the universe. Steve Warren is unique in the sense that he found the first redshift 4 quasar and the first redshift 7 quasar. Pat Osmer was involved in a number of the high redshift quasars and wrote one of the most depressing papers I've ever seen in my life. Which, by the way, well, I'll tell that story later. Richard McMahon was with the Cambridge group working on the APM scanning machine, found a number of high redshift quasars. Jim Gunn developed the Sloan survey, was involved working with Maarten at Palomar. And then Xiaohui Fan and Michael Strauss working with the SDSS. And then recently, in the last 5 years, Chris Willett with the CFHT, combining infrared and optical data, were able to go to beyond redshifts 6 to later 7. I was looking for a picture of Maarten, but I could only find this one. This picture was taken by Maarten. I'm showing this for 3 reasons. One, first, do you know where this is taken? Can you identify it? It's the Cassegrain cage of the 200-inch. Okay, that's a 200-inch mirror right up above there to show the scale. I wanted to show this because if you understand the lighting and the perspective and the difficulty of getting a position to take a picture, Maarten had a real, I think, calling as a photographer, but he didn't pursue it. Also, I wanted to point out a somewhat unsung hero, and this is Jim Westphal, who really, as much as anyone, brought CCDs into astronomy through his leadership of the Wide Field Planetary Camera and the HST, and providing CCDs for Palomar. And this is the 4-shooter well. It goes up into the CAS, which we used to do the survey. Okay, what's next? Okay, Sloan survey, which I think had a huge impact on the high redshift quasars. First time I saw the schematics of this diagram, I didn't think it was much. Couldn't believe they were actually going to build, have this sliding house go over this telescope, but it's worked out very well. This is the quasar selection algorithm. When I was working with Maarten, I had this line, if this, then observe. Okay? This is Gordon Richards, who is my postdoc, and this is what's done. I've never really understood this, but Gordon says it really does work. And somehow it does observe that object, and there are 40 flags, and you work them out, and you can eventually figure out whether to observe it or not. I showed this picture of plugging a plate. You can see the plate is about 1 meter across. There are 600 fibers. I'm showing this because this is one of the directors. I think this is a posed picture. I really don't think Richard Crone ever plugged any of these plates. But it makes it look like the director is a hard-working person in Sloan. There's actually a crew of people, again, some of the unsung heroes of science, that every day plug 10 of these plates, or 9 of these plates, by hand. We initially thought of trying to do it robotically, and we would get them in very easily, but then we had to unplug them. And once you start moving things around in a telescope and you say to a robot, go unplug this fiber, okay, and then 13 come out in various state of damage, so it had to be done manually. And then recently, I'll show spectra a little later, 2011, the Redshift 7 barrier was broken by Daniel Mortlock and Steve Warren and their team. Okay, so let's look at by high redshift now. I'll be talking about redshift 4 quasars. Here's the rate of discovery, the year of discovery versus the quasar redshift. And I've indicated in green the objects discovered by Maarten Schmidt. Okay? So you can see that, when you talk about quasars and Maarten Schmidt, everyone thinks about 3C73, 273. Some will think about 3C9. But actually, if you look in the, these are the highest redshift quasars known, and, Maarten had discovered a large fraction of them through the 1990s. Then in the SDSS ones are indicated by the red, and then you can see there's the Redshift 7 one. These are infrared based detections. Okay, to just show you an idea of what we've been able to grasp in the last 2 decades, in 1987 there weren't any Redshift 4 quasars known. Now, these are in bin sizes of a tenth. We have over 400 between Redshift 4 and 4.1, right? I mean, so in terms of can we detect them, but we can actually build samples to actually study their properties. Here's the discovery. You can see the enormous improvements since the year 2000, right? We're dibbling in here with half a dozen a year or so, and I think we're now at the rate where we'll be discovering on the order of 100 objects over redshift, 100 quasars over redshift 4 every year. Okay, quasar luminosity function. Are there arrows on this? How do I go back? Is it the back arrow? The back arrow makes sense. Okay. Early work by Maarten Schmidt that's just been discussed revealed the rapid growth in the quasar numbers. I did want to show this. Maarten referred to this earlier. I'd really like to read the quote. This is the 1970 paper that some people think it's famous because it showed the evolution of the luminosity function. It's really most famous because it allowed Quasar to be published. It says here, and Chandra was clearly anguished by this decision. You left out a key phrase. The Astrophysical Journal has up to now not recognized the term quasar, and it regrets that it must now concede. Dr. Schmidt feels that, with his precise definition, the term can no longer be ignored. Okay. So there's been a discussion of this. Well, that was the back arrow, I thought. Sorry. Oh, these are the arrows. Mm-hmm. Okay. All right. Okay. So the luminosity function rose very rapidly up to a redshift of 2. I was hired in 1981, and I was really looking forward to finding lots of redshift 4 quasars. And then in 1982, Pat Osmer wrote a classic paper that evidence for a decrease in the space density at quasars at redshifts above 3.5. Pat did a very careful survey of the sky using plates, was looking for quasars between 3.7 and 4.7, and he based this work on extrapolating luminosity functions, and he expected to find 9 to 22 objects and found 0. Okay, so this is very discouraging to a young postdoc who had just been signed on to find all these things and become rich and famous, or at least famous, and I was found before we even started the survey that they weren't there. Since the 1990s, there are several groups, or in the early 1990s, Steve Warren, Maarten Schmidt, George Rogowski had started to detect sufficient numbers. By sufficient, I mean on the order of a dozen, so that you could actually measure the decline, not just say it has to be at least this much at high redshift. And samples of quasars at redshift of 5 to 6.5 have now been assembled. Okay. So here are the early measurements. These are all based on typically, Maarten's work had 90 quasars, but it went down to about 2.8. This, I don't know if I love it or not, but it's really spectacular. This is 100 quasars, 100 quasars. 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 1 by Steve Warren, Paul Hewitt, and Pat Osmer. From their work, this is look-back time, so this is the current day, and this is the start of the universe, and this is the number density. It's really spectacular when you plot it on that axis. Okay. This is the work from the GRISM survey. These points from, in 1995, Schmidt et al. This is an earlier work on the low redshift quasars. And this is George Rogowski's student, Julia. Is that right? Julia Kennefick. Here's the redshift 2 luminosity function. And here are the points. Let's see. These open squares, so these must be these 4 points. These two are, I think, Schmidt 48-inch survey, multicolor. And what amazed me was that the fact that all three agreed, more or less. And they were so radically different. 2 of them were multicolor selections. Maarten's survey was a GRISM survey using low-resolution spectra and showing this very steep decline. And, okay, so then the Sloan Digital Sky Survey started working. This is the first one in 1999, led by Xiaowei Fan, who was a graduate student at the time. Here, okay, so this is the Warren Hewitt Osmer. This is Maarten's survey, and then the SDSS. And you can see, to me, this is an amazing agreement, considering all the selection effects and the different techniques that you can see. And this is a logarithmic scale, okay? This is a factor of 10 in the number density. And this is an updated one by Gordon Richards in 2006. And again, you can see Gordon was able to get quasars at essentially all redshifts up to about redshift 5. And here's a point from Xiaowei Fan there showing the rise and the fall of quasars. Okay. And what's the current status? Here's this, I think, Richard, you showed this plot. This is from McGreer et al. It's published, I don't know, 3 or 4 months ago. This is a quasar luminosity function at a redshift of 4.9. You can see the broken power law. And again, Richard pointed out the key problem that had been confronting us for 20 years, that there was this discussion by almost all people in the field about the flattening, meaning that as you went to high redshift, there seemed to be more, the power law did not fall as swiftly, but that problem was caused is because the knee was essentially, we were being cut off, we were going slightly below the knee and interpreting that slope instead of that slope. So it does appear that when you go to high redshift, that this slope does continue at more or less this minus 3.7 or so. And again, these were very important points because they were low luminosity at redshift 5 to show that the slope is compatible with the lower redshift values. Okay. Quasar energy mechanism, the growth of supermassive black holes. One of my favorite papers in this field was by Ed Turner in 1991. The first redshift 4 quasars found in 1987, and by 1991 the sample was up to about 15, including a quasar that was found in Maarten's survey at a redshift of 4.7. And Ed recognized that if you were forming these very massive objects that early, what were the implications? And so this is a really excellent paper. I'd recommend anyone who's interested in the development of the field read this. When we started finding these redshift 4 quasars as a naive young postdoc, I said, we're going to find all these distant objects, and we're going to find that they're so early in the universe that there won't be any metal lines because there's no time for the metals to form. I was confident of that. Well, it turned out that the quasars we were finding had very little difference from the lower redshift quasars. And even at redshift 7, okay, this is the Mortlock discovery 2 years ago, the black, look at that drop, isn't that impressive? The red line is the SDSS composite at low redshift. Okay. And, there's clearly metal enrichment very early on. The lines look essentially the same. If we just cut off this and I change that wavelength scale, you would say, oh, it's a redshift 1 quasar or something. Okay. This next diagram is a little complicated, having to do with X-rays. If you look at redshift, this is sort of looking at the relative contributions of X-ray to optical. Okay. And you look at it over the age of the universe, it looks like that ratio essentially stays the same. In other words, if you had that ratio remaining the same, all the points would lie along here. Okay? And so there's no strong evidence that that is changing. I'd like to talk about, let's see, how am I doing here? High redshift quasars in the intergalactic medium. 1971. The observations of the most distant known quasar, 5C 5.34, by Roger Linz, revealed the Lyman-alpha force. And I think this is a really important paper, and I wish it would get more references. I'm tired of reading things written by people like me that say, the Lyman-alpha force, Schneider 2000, et cetera, is well known to be such and such. And it was Roger Linz that found this. And this is the spectrum. Maarten earlier, Todd and I were marveling at how you could make these interpretations on these photographic spectra. This actually is really quite an impressive one. This is Lyman-alpha. This is blue. And you can see all the white lines appearing there. That's the Lyman-alpha force. And Roger did interpret this as Lyman-alpha observations and did all kinds of tests about how many are on this side and this side. So this is really the discovery of the Lyman-alpha force, giving us a high redshift quasars, giving us a new view into the universe. 25 years ago, the first quasars are found redshift 4. Of course, people knew about the Lyman-alpha force, and it seemed to be becoming thicker. By redshift 4, this drop was about 50%. So here are the 4 of the quasars discovered around 1990. You can see the very asymmetric shape of the Lyman-alpha line, the drop due to the absorption becoming quite large. Okay, so most of the flux is being absorbed. These are all between redshift 4 and 5. And then in 2001, a number of groups, I just pulled this one from Becker et al. 2001 is a nice comparison of 4 quasars. This is at 5.8, 5.82, 5.99, and 6.28. And you can see the slow, the steady decline in the amount of transmitted fraction. Okay. And this was the long sought-after Gung-Peterson effect, which was done because of Maarten's observation of 3C9. Am I telling the story correct, Maarten, that Jim and Bruce saw your spectrum and then said, oh, we see flux below Lyman-alpha, therefore the universe has to be reionized. And so at some point, when did this reionization occur? And high redshift quasars have given us some information here. Here's a plot from a paper by Xiaoyi Fan in 2006, showing this is the optical depth, bluebird of Lyman-alpha, and you can see it's slowly increasing, and then it rapidly goes up. Of course, by the time you get to optical depth 5, it's very hard to place anything but lower limits. So we certainly are seeing the end of the reionization era around redshift 6. Okay, redshift 7 and beyond. Finding redshift 7 bigger than 7 quasars presents several challenges. There's essentially no radiation shortward of Lyman-alpha, which means, it occurs, there's no radiation shortward. Lyman-alpha occurs at 1 micron, so you've got to have infrared detectors. The objects are faint, J bigger than 20, and the objects are exceedingly rare. The LF at Z equals 6 is about a factor of 5 below redshift 5. And that's accelerating. If you looked at those plots, if you look from 4 to 5, to kind of 6. It's sort of straight on this logs, whatever it is, plot. But when you go to redshifts beyond redshift 6, it's falling even faster. And so you require sensitive wide area infrared rays. Okay? And so when I look at this, I say, well, this is the same thing that happened in 1980. Okay? There's no radiation, or there's little radiation below 6,000 angstroms. We had to go to red-sensitive detectors, which were a challenge at the time. Where are we going to be able to do this? They're faint. The objects were down around red magnitude of 1920, and they're very rare. Okay, so we had to go to big area detectors. And so it took about 10 years of concerted effort before that was found. We've got the same problem today. Okay? We've got to go to redder detectors. The objects are getting fainter. The objects are more exceedingly rare. Okay? And I hope that when we have a conference in 25 years to discuss high-redshift quasars, people will be able to give a talk like this saying we now have thousands of redshift 6 and 7 and 8 quasars, because those people back in 2013 just didn't have the imagination of how to proceed on to that. Okay? So there are a number of surveys that are now ongoing. I won't go through all of these, but I think there's a hope in the next decade or so that infrared detectors will be able to cover enough area, will be able to be sensitive enough that we'll be able to pick up these very high redshift objects. Okay, so what have we learned from 25 years of redshift bigger than 4 research? Well, the number density of quasars starts to drop dramatically at z equals 5, and the rate of decline is accelerating. Okay, remember that plot, 4, 5, 6, and it's really falling off. Am I out of time? Close. Okay. Billion solar mass black holes can form within a giga-year of the Big Bang. Okay, this is alluded to. How do you fuel these things, grow these billion solar mass black holes that quickly? There doesn't seem to be any evidence of a change in physical processes of black hole accretion over the age of the universe. Rapid metal enrichment occurs in the environments of supermassive black holes, and the key element of H1 reionization seems to occur at redshift 6 to 8. So I think that's a pretty good set of accomplishments for 25 years. Okay.
Thanks, Don. Are there questions?
Don, is it possible that part of this apparent evolution is due to an increase in the fraction of
Obscurity?
truly obscure quasars?
Yes. Yes, and you could imagine a scenario where it just takes time for them to blow out. That certainly is a distinct possibility.
Is there any evidence for that, or is it just...
I think, Richard, where's Richard at? You showed a plot, right, that showed the fraction of obscured quasars as a function of... Oh, that was luminosity. Oh, okay. The next speaker, I've been told I have to... Okay.
Any other questions? Judy.
That's right. He really is an unsung hero. Back in the late 70s, and he was getting these early CCD developments that were being tested at Palomar for that. And certainly these things would not have been possible without his effort. And it was more than just pulling a few strings. He actually went observing, and he really was a key person, and I'd like to see him recognized by the community for his contributions to this field.
No others? Okay. Let's thank the speaker again.